picture yesterday, I might have made some brief references that we are going from something that has to do with force, and hopefully I talked about the effectiveness of force, that the acceleration is something we can observe, and the force is something that you do, and tried to make a reasonable relationship to how net torque would work, right? Some of the same things. When we apply torques, that's something we do. We can observe accelerations. The difference with angular accelerations is that we can definitely observe speeding up and slowing down. That's what was over there. Change in direction is a little harder to observe. What we really have is a change in the axis of rotation instead of a change in the direction. So imagine you can spin a football by throwing it, and that's a spiral, and it spins through the points. But if you kick it, it tumbles end over end. That's a different axis of rotation. You could probably imagine that applying a torque under those circumstances could change the axis of rotation from one of those to the other, or both at the same time. So what I'm arguing is that we don't necessarily have the same kind of change in direction that we have for a translational motion of an object, where it just makes a turn around a corner. Our change in direction is different for things that rotate. But we're going to have something in here that we're calling the moment of inertia that is dealing with how effective the torque is. And things with more inertia are more difficult to change. In fact, that's exactly how I describe my fifth period, that they have a lot of inertia. They're difficult to get moving. And they appreciated that because I think they understood it tremendously. You guys, in some circumstances, not very different, but you're a little more susceptible, sixth period, for whatever reason. And I think I gave this a symbol, right? We said that we're going to use a capital I for moment of inertia. You see some symmetry here, don't you? We have more than two, but we have at least two other relationships that are based on inertial mass. For example, let's see if you remember, kinetic energy, 1/2 mv squared. The m in this expression is about the inertia of the object, not its gravitational mass. We know because we dealt with work, and that's where it came from. You do work on an object and you change something about an object, required a force to change its velocity, that's inertia, right? So this is the inertial mass. Would it be too big a stretch to consider that there might be a rotational version of this? I mean, if you're trying to invent what you think that relationship would look like and using only this as your data point, what do you think? I think there'd probably be a 1/2. What else? Probably an I. What else? Instead of v omega squared. Does that seems like a reasonable deduction. I don't know if it's true, but it's a reasonable deduction. Similarly, momentum. We know this is based on inertial mass because it's about it's about how we changed the velocity of the object to give it momentum. It's inertia while moving, so it's kind of even in the name. What do you think for angular momentum? It seems not unreasonable that I omega might be a way of expressing the angular momentum of an object. I'm not proving any of that. What I'm saying to you is that those are reasonable deductions. I think I can prove at least one of them. And I probably could prove them both as not just reasonable deductions, but the way in which we could measure it. Let's use kinetic energy as our example. It's the easiest one for me to show this about. It'll also help us figure out what this is, okay? So I want to start with something very, very easy, a big spinning disk. A disk is nice because of its uniformity. It has uniform properties. And consider a moment when this is moving. So the whole disk has angular speed omega. And from there, consider that there is a piece of the disk, not just blue tape, but that we have a piece of the disk. Like I could cut out a small square of the disk and then just put it back in there after I painted it blue. Everybody okay? That piece would have mass m. And because it's part of the disk, at this instant, it would have a velocity v. All good so far? Now, if I grab my tool and cut out a piece on that inner circle. This piece would have mass. And if I put it back in the disk and it was spinning, it would also have a velocity too, right? But this velocity would be less than the other velocity. In fact, if I named this piece 1 and this piece 2, then you could probably imagine I could go around and take the entire disk and break it up into lots of pieces, label it, put it back together, and when it's spinning, each piece would have its own mass and its own velocity. Does that make sense? Now, 1/2 mv squared is invariant. It is the kinetic energy of anything that's moving. Those two pieces at any time are moving when it's on the disk if the disk is spinning. Agreed? So if I want the total kinetic energy of the disk, can TKE be just a temporary thing we say for a few minutes? It would be 1/2 m1v1 squared, the mass of one piece, plus 1/2 m2v2 squared, plus, and then I could just keep doing that until I used up every piece of mass of the disk. Everybody follow along? This would be the total kinetic energy of the disk. Is that fair enough? Everybody following my argument? Now, there's a way to write this, right? That there's a summation notation that would allow me to write this a little bit more compact-like. So I could write this as the summation, starting using an index. An index just allows me to piece through the whole thing. So starting with piece number 1 until piece number n, where n represents the last piece. I don't know how many pieces it is, but I don't think I have to write the notation out. And this would just equal 1/2 mi vi squared. This is a way of writing it. Is that okay? Now, just looking at that, the way it's written right now, I notice that in my summation, every term would have a 1/2 in it, right? They'd have to. So I'm pretty confident that because of the way algebra works, I can take away the 1/2 from every term, factor it out. That way I don't have to multiply mv squared and then multiply by 1/2 every time. I can just do the sum and then multiply by the 1/2 at the very end. So I'm going to factor out the 1/2. Now, if you don't know where I'm going with this, that's okay. Some of you do know where I'm going with this, and that's good. Because the idea here is to find other things that are common about the object. I have something else that's common. Each one of these velocities is related to how fast the disk is spinning. In fact, we know from prior experience that the individual velocities are based on how fast the disk is spinning and where the piece is relative to the axis of rotation, right? So in the example drawn above, there is an R1 that could be used to describe where piece number 1 is. And there is an R2 that can be used to describe where piece number 2 is, and so on and so forth. Wouldn't there be an R for every single piece of the disk? So I think we could rewrite our summation with that in mind. Does that make sense? Do you kind of see what I've done there? Now, I'm noticing, I hope you're noticing, that every single term would have the same omega in it, since the entire disk would have the same angular speed. So I think I can factor that out. Now I have to distribute the square first. But I'm going to do that in one step if that's okay with all of you. So that would give me 1/2 out front, the summation of m and r squared and omega squared out here. I can factor it out to either side, it doesn't matter, right? But by doing it this way, do you see what I'm getting at? That I think this is our inertia. If the symmetry of these relationships work, and I think they do, this should represent our inertia. I want to point out, look at the features of this term. Does it not include in it the entire mass of the object? Right? Mi summed through the whole thing would include the entire mass of the object. But does it not place preferential treatment to pieces of mass that are further away from the axis of rotation? And does it also make sure we understand that that part's more important, right? The distance away makes a bigger impact on the inertia than the mass does. If I double how far the piece is away from the center, that adds 4 times the inertia. But if I double the mass of the piece, it only doubles the inertia. So obviously the shape matters. And isn't everything there about the shape of the object and not about its motion at all? Right? The other parts, this is about motion. This is what's happening to the object. This is about the shape of the object only. Do you notice that? Of course, this is based on a specific axis of rotation, because all of the r's that are here are related to whatever the axis of rotation is that we've chosen. Good so far? Now, you have no reason to believe that this is true. But I'm providing evidence, just algebra evidence. So what I'd like to do is see if we can't demonstrate how this might be true. Does that make sense? Now, doing that might be hard. I'm not going to take my disk and actually break it up into pieces. But I am going to try something that I think we can do together. The accepted moment of inertia of a long rod is either 1/12 or 1/3 ml squared. It depends on whether we're dealing with the end of the rod or the middle of the rod. Now, eventually I'd like to prove that for you. But today, I'd just like to see if maybe we can use it as a starting point. So let's talk about the end of the rod. And let's just write over here so we have it that it is accepted that the moment of inertia of a rod about its end is 1/3 ml squared. We're trying to see if our little summation is a reasonable way of calculating the moment of inertia. Now, I want to do this by just using a summation, and there's a problem with what we're about to do. And I think you'll figure out what that problem is pretty quick. But a summation requires that I take an object and break it up into pieces. So we're going to break an object up into pieces, but we're going to do it mentally. Like I'm not actually going to break a thing up. And that's why you have your meter sticks here, because the meter sticks will be helpful for us because I have nice little markings all over them, right? So I want you to consider, I'm going to try this for breaking it up into 5 pieces, okay? 5 will go pretty quick. We're going to do this twice, by the way, once for 5 pieces and once for either 10 or 20 pieces. I'll leave that up to you, okay? Now, what I mean to do is to take a look at this and quite literally consider 5 pieces. Not perfectly distributed. Let's do better, Mr. Shelton. I think it's possible. I'm not going to do it again. Yeah. That one bugs me worse than the other one. All right, that one's fine. All right. I'm taking a meter stick, I'm going to break it up into 5 pieces. I'm going to say that this is 0. Okay? I'm also going to say that it's not a meter stick. I'm going to say it's got length L and mass M. I want to get something that is comparable to 1/3 ml squared. Okay? Now, if I break my meter stick up into 5 equal pieces, how long is one of those pieces compared to the whole thing? What's that? Well, it's 20 centimeters, but that's not what I asked.
1/5 out.
What's that?
1/5 out.
1/5, right? It's 20 over 100, or 1/5 of the entire length. Now, I'm saying this to you because, hear me out. I'm going to assume that the center of mass of each piece is in the center of each piece. Okay? Now, we're going to try and build a summation. And our summation has to take and add up from the first object to the fifth object the mass of each piece times the distance from the axis of rotation to where my mass is squared. Let's take a look at that first piece. If the entire thing has mass m, what is the mass of the first piece? All right, so 1/5 m, or m over 5, because I'm breaking it up into 5 pieces. Okay. How far away is the first piece's center of mass from the axis of rotation? Sure, 1/10 of L. You guys see that? Any question about how I got 1/10 of L? All right. Let's go to the next piece. I think there's going to be some repeated values here. Do you see that? So if I go to the next piece, what is the mass of the next piece? M over 5. All the pieces should be the same. If I'm dividing it up the same, I don't have to divide it up the same way, but it seems like a reasonable thing to do. So I'm going to go with m over 5 again. Well, not 5 over m over 5. All right, now this was R1, but this is R2. How far away is R2 from the axis of rotation? Excellent. 3/10 L, but then squared. I see a pattern developing. Do you see a pattern developing? Now, there's going to be 3 more terms. But before we start getting into our 3 more terms, can we start collecting the things that are going to be in every term and just take them out front? All right, name something that we know is going to be in every term that we can take out front. M over 5 will be in every term. What's something else we can take out and put at the front? We could take L squared over 10. That's fine. But it'd be 10 squared, right? So L squared over 100. Is that okay? Now that would leave for the first term just 1 squared. The second term, 3 squared. What do you think that third term is going to be? I mean, it makes sense, right? 1, 2, 3, 4, 5. Next term? 7. Next term? And we know there's no term after this because we broke it up into 5 pieces, but also the term after this would be 11/10. That'd be longer than L, and we're only going to stop at L. All right. So this looks like 1 over 500 ml squared, and 1 plus 9 plus 25 plus 49 plus 81. Get busy. I ain't adding. That seems like something for a student to do or a TA to do. All right, now the accepted value is 1/3. We did not get 1/3. We got 165 over 500. What is 165 over 500?
33 over 100.
It is, but that's 0.33
That's like
ml squared. Now, that's not a third, by the way. You'll notice it's clearly not a third. But it sure is close to a third, isn't it? Now, we knew this wasn't going to work. We knew before we started it wasn't going to be exact. And part of the reason we knew that is because, look, we made an assumption. We assumed that we could treat this whole thing as if it's a point mass located here. But we just showed that this part of that mass is contributing more to the moment of inertia than this part of that mass, right? If I want to get closer to the actual value, I should break this up into smaller pieces. Like, I bet if I break it up into 10 pieces, I get a better answer. 20 pieces, I probably get a phenomenal answer. 100 pieces, I bet would be great. I mean, 1,000 pieces are just millimeters. Now, you guys are smart people. I hope you're reasonable enough to realize that you could probably get a computer to do this for you easier. Me making you do it is me saying to you that it's better that you try it out and see. 20 seems like a lot, though. I think 10 is okay. Do you think you can do 10 real quick? Like in 4 or 5 minutes? I mean, once you understand the pattern, it shouldn't be hard. For example, let's see if we can just do the first 2 terms real quick, shall we? First 2 terms. My picture's not going to work anymore because it's got twice as many things going on. So suddenly, I'm going to break this up into 10 pieces, and I'll place the centers, there. So if we're breaking up into 10 pieces, what is the mass of an individual piece? There we go. So m over 10. Excellent. What is the distance from the axis of rotation to the first piece? What's that? 120 L. Yeah, 1/20th L. We okay with that? You understand where that came from, right? We sure? Well, it's 5 centimeters, right? And the whole thing's 100. So it's 5 over 100, which would be 1/20th. Okay.
Sorry, I was just quoting.
Oh, no worries. Our next piece, still m over 10. But now we're not 120. Where are we? 1, 2, 3 20ths away. Do you see a pattern yet developing? So if you see a pattern developing, can we maybe factor out the things that we know are going to be the same for all of these? Like maybe 20 squared, 400 times 10, 4,000. So 1 over 4,000 ml squared. And you can figure out what goes in here, starting with 1 squared and then 3 squared. And then, I'm seeing a pattern develop. And you guys who have pre-calculus, used to be called algebra 3, they used to do what was called series and recursive formulas, but I believe it's no longer part of the curriculum. I know it's not in, I don't think it's in AP pre-calc, but there's something to be said for this. If you are good at iterative and pattern matching, you'd be good at this. And recursive formulas are formulas that can be used to tell you the answer of a series without having to actually work out the series. But I'm just talking to fill up the dead air so that you guys can tell me how close we get. Anybody else get that?
Yeah.
Now, yeah.
I was wondering, so since we know that the mass will always be the same for each piece, can we just pull out that mass, like in the summation notation?
Except that, and I wanna preface this by, we assumed something that had a uniform mass density. If you had something that maybe gets heavier from one end to the other, or something that does not have uniform mass density, every piece is a different mass, even if you are selecting the same volume piece. Does that make sense?
Yeah.
It is not uncommon for them to give us an expression for the density. that may change from one side to another. Does that make sense? Okay. You got 0.3325 ml squared. So yes, we're getting closer to a third, but we're not going to make huge steps here. We doubled the number of pieces and just gave us one more decimal of precision. So you understand that it might be a long way to be able to get to a third. Now, so if you don't understand why I'm saying that, let me be very clear. Moments of inertia add together. If you have a complex shaped object, but you know the individual moments of inertia, you can find out the total moment of inertia. Let me give you a simple example and then maybe a complex example. I'm going to make like a cartoon barbell. You know, they always had the big circles, big spheres on them. And they were, yes, okay. And they were maybe separated by some rod. So I'm drawing it different colors on purpose, but can you imagine one of these with the big circles on the end? Not what, I mean, you guys clearly are hitting the gym all the time. It clearly shows. And I see all the gains out there. I'll just look down. But can you imagine something like this? If you can't, can you imagine that we could probably grab, a couple of things that are round and stick it on something that is long and then spin it? We have expressions for the moment of inertia of a rod about its center. That's the moment of inertia of a rod about its center. And we have an expression for the moment of inertia of a sphere. If we assume a solid sphere, that would be 2/5 r squared, where r represents the radius of the sphere. All right, this is all the stuff we talked about yesterday. Moments of inertia have no direction. They're not vectors. And they're not like center of mass, which requires reference, except for the axis of rotation. So when we talk about moments of inertia, if you have three objects, you can just add together their individual moments of inertia to get the total moment of inertia. So let's say we want to take this and spin it about its center. Well, if I know the moment of inertia of a sphere, and I know the moment of inertia of the bar, well, I could probably figure out the moment of inertia of this combined object. There's just one problem. This moment of inertia is the moment of inertia about the center of the sphere. And we're not spinning it about that, we're spinning it about this point. Lucky for you, well, I'll say lucky, but it's not lucky. It's just more work for you. There exists an equation that would allow you to move the axis of rotation from your moment of inertia. It's called the parallel axis theorem. And it would let you take the moment of inertia at the center of mass and move it by whatever distance you needed to shift the axis of rotation, even to a point outside the body of the object. So consider this arrangement. I know the moment of inertia of the sphere is 2/5 mr squared, about its center. But I'm going to shift it from here to here, a distance of L/2, by the way. You follow what I'm doing? If I wanted to find the new the new moment of inertia for a sphere that's being rotated a distance L/2 away from its center, this would be the new moment of inertia. This is called the parallel axis theorem. It allows you to shift the moment of inertia to any parallel axis. You notice how I keep stressing parallel axis. For a sphere, any axis is parallel to its center, right? Maybe that's not right. Maybe you don't understand what I just said. But if you have a sphere, any axis will be parallel to its center because it's spherical. It's the whole point of a sphere. It's symmetrical in all directions.